So these logs here, I mean, as a classic 8-inch three-sided log, what would they rate out as, sort of as an R value in terms of entering it into the program?
Wood has an R value about an inch, 1.5 per inch. So
Okay.
an 8-inch log would be about an R12.
Okay.
And you can measure those, get an average of them, see that they are about 8 inches, a little shy on those ends. And the program will accept log as a construction type. Also, we notice that the floor actually starts about here. So the rafters are hung off this part of the floor, and then we'll look underneath and try to determine how much insulation they put in this floor. So we're probing this floor to see what we have for insulation in here, and it appears to be about a 10-inch cavity. So we've got about 9.5-inch cavity there, and it feels like it's filled with fiberglass insulation. They have this particle board over the entire floor, so it's tough to actually get a good visual, although we have found one spot over there that we'll try to take a look and see if we can actually get a visual on what's in this floor. All right, so we are able to see here that we do have fiberglass in this floor. And by reaching in there, we can see that it does fill the entire cavity up to the bottom of the floor. I'm touching the bottom of the floor now. And as we pull our hand out, we want to make sure that we fluff the fiberglass back up. So it is a full 10-inch cavity filled with about R30 fiberglass.
What we're looking at here is we've got about a 10-inch floor joist, and so it's about an R30 fiberglass bat. For the era that this was built in, that was pretty typical. This was built in the mid to early 80s. Current HFC minimum, state minimum suggested R values for floors is R38, which would mean going with a 2x12. So it's highly likely that when Paul runs the program, it'll say that an additional layer of insulation might need to be added here. The program is going to factor in all the different parts of the house and then make assessments on where the greatest gains are. This could be one area where we could see that adding 2 inches of insulation onto the bottom of the floor could make a big difference.
When we get up to the dormer on the second story, we can see that that's all frame walls. So we'll try to determine from inside the thickness of those walls and how much insulation was put into them.
Everywhere we go, it looks like the roof is at least well ventilated.
So as we're walking around the outside, we also see that we've got a drop-down floor here, a floor that's lower than the rest of the floors in the home. And it looks like it's connected to a septic system here, so we're assuming that's a bathroom. And see if we can determine how these walls and this floor itself is insulated also. Okay, so this.
Oh, there we go.
The walls are 12 inches here, and we appear to have about an 8-inch wall here and a few inches of foam on the inside, and then the wood for siding.
I could see some room for improvement, at least with this doorway. It could be air sealed better and have more insulation on it.
Yeah. You know, everything you want to improve, but this again, it's such a small portion of the area, but it all helps.
Yeah.
You know, every little piece that you take care of is another little piece of the puzzle that makes the house function better. Air leaks are a direct relationship to heat loss. Heat loss is a direct relationship to energy efficiency. So if you have a lot of heat loss, you have a lot of energy loss. So we do have some water staining on parts of these log walls here, and this is an indication of moisture leaks. And typically the moisture leaks, you ask the homeowner, does it leak when it rains? If it doesn't leak when it rains, then chances are this is moisture caused from condensation. Hot air is rising up into cracks along the area of the house here, getting up into the roof cavity or getting up into a cold area, condensing, and then as it warms up in the springtime, that comes back down as leaks within the house.
You can see there is a vapor barrier, but it's not sealed. It's kind of loosely folded, so there's a way for air to get up and inside there all winter long. So to fix that, you guys would probably have to pull all that off. and apply a bead of sealant, remove it, and make sure it's nice and tight.
You can see we do have the bit of a drop floor here, but this is where that box was for all the plumbing underneath the home that we took the panel off of and we're able to look inside. So that's a different portion of the house that will be broken out in the Act 1 program.
So you would go along and you would measure and record square footage of every wall, write that down then, and then enter that into the program later.
Correct. And most of the time, if the walls are the same, they're all entered as one entity. Any walls or floors or ceilings that are different then get entered as a different entity or their own separate entity. A lot of times homeowners are surprised to find out they have triple pane windows. Double pane windows are decent windows. The triple pane is better. Double pane usually rates out at about an R value of 2. A triple pane is going to be an R value of 3 or better, up to 5 or 6 now with some of the better windows that they have. But you're still only gaining an R value of 2 or 3 in a small area. Whereas if you insulate this whole log wall here from the inside, you're gaining much more square footage, and you're going from an R12. If you add another R19 to it on the inside, then you've gone to an R31, much different R value gain over a larger area than just doing a few windows. And these are 6-inch walls.
And all this is paneled as well, so none of this paneling goes all the way through to the outside.
We're looking at the gambrel roof here, which is about the 12-inch wall we had here. It's a 12-inch wall, and then they've added a window into that, giving us a little thicker area there. If we head out this way, we can see that the end walls are 6-inch walls. So we've got R19 there, and we're looking at the different connections between the house and the wall. Joints in these type of homes tend to be problem areas, tend to be where the floors and the roofs come together. If they're not connected well or sealed well, then that's an area for good air leaks. And that could be where we've seen some of that staining down below from the condensation building up.
So any place you have a transition, you know, floor to wall to ceiling, you'd see a joint like this, and you'd want to take a pretty good look at that.
So now we're at the transition between the log part of the home and the frame part of the home. This is the back addition on the house that we saw from outside. So we're looking at what is the thickness of this wall, how much insulation do we have in it. So we'll open the door and we'll measure the thickness of the wall at the door. Now it appears to be a pretty thick wall, but the siding is actually recessed here, and so we'll get a measurement on that at about 2 1/4. We'll come in from there, and we'll find that we have about a 6-inch wall, 6.5-inch wall here, so that gives us an R19 insulation. A 5.5-inch stud gives us an R19 insulation inside. So these walls here have an R value of 19 minus the stud cavities. We'll put the R19 into the program. That'll give us our R value. Then while we're here, we'll look at the door. This is a homemade custom door. It's wooden. It's not solid core, as we see a lot. This is measures about 2.5 inches. So we're figuring this door has an R value or a foam of about 1 inch of XPS or EPS foam in it. We're also able to see a crack in the door here and see that there is foam, board foam inside this door.
What would this door typically rate out at then?
It's hard to say. I mean, you can add the wood. The program is not going to let you put this door in. You're going to have to make an estimate as best you can. But basically, it's going to be, say, 1.5 inches of wood, which would be an R value about 2 3/4, and then you've got your foam, which is about a 3, so you've got about a 5.
Okay.
And this fan is made to run continuously for about 30,000 hours. One switch in the house running one fan can ventilate the whole house. It allows for air to be pulled in through here and will dry the entire house out in an average size home. There's different thoughts on ventilation. Should I get a big fan that gets all the moisture out really quickly, or should I have a smaller fan that runs continuously and more of an even flow? And I think the idea of a small fan with an even flow tends to keep the levels of cleanliness or the fresh air in the home at a constant level rather than having peaks and valleys as it a higher volume fan kicks on and off.
Well, this is a big stove. I mean, it could hold quite a bit of wood. So you would look at this as a primary heating appliance. How would that factor in?
Basically, Ilya, the way you look at that is you have to talk to the homeowners. What is their main source of heat? Does this stove have the capacity to heat this house? Is it in a location in the home where it can work as the main heat source for the home? And this appears to be the main heat source, and then talking to the homeowner, they stated that this was their main source of heat. This is what goes 24 hours a day. This is what they use the most for the home. A lot of times when you have a boiler or forced air furnace in the home and a wood stove, it's again talking to the homeowner, how long are they gone, how do they treat the house when they're at work all the time. So do they let the furnace or the boiler take over, and is it the wood stove or is it the forced air furnace?
So what you're doing is you're factoring in like a pattern of energy usage. So this would be assigned a certain value versus a boiler versus a furnace. And so when you would enter that information into the program, and it would break it down then based on efficiency and usage. So normally in a rating, Paul, you would basically go through and measure all the exterior square footages to figure out how much heat you're losing through different parts of the house. And then the next step would be to calculate how much volume of air there is in the house and the amount of air leakage. But that would require depressurizing the house with a blower door fan. I don't think we can do that today because of the wood stove. Is that?
No, we can't. You cannot do that if you've got a wood stove or a pellet stove going, because as you depressurize the house, you'll be pulling air down the stack, and all that smoke will come right into the house and fill the house up with smoke. When you need to turn off the heating system, such as the boiler, furnaces, toyos, or you can pull the flame out or cause damage to the home from the flame.
So assuming you've done an air leakage test, a blower door test on the house, and you've got all the exterior square footage and the Acorn program runs the numbers, what are some typical things that come up as improvements?
Every house is different. You never know what you're going to walk into till you get there. This home is complicated. You've got different additions. You've got even the log walls have different insulation values on those. The windows are different. The doors are homemade. You've got quite a bit of different components in this house to put together. And that's why it's important to get your facts and your insulation qualities as close as possible so you can get a more accurate rating, guiding the homeowner in what's most cost effective to do. Well, we're here to complete a blower door test. We've got the heating system shut off. We've got all the doors and windows to the outside closed and all the interior doors open, so we're ready to depressurize the house. When we talk about depressurizing the house with this blower door, we're going to be forcing air out of the house, equal to about a 25-mile-an-hour wind on all sides of the house. And as we send air out, we'll be able to pull air in from the different leaks and cracks and unsealed areas in the home. And here we go. You can see now that the blanket is pulling itself in. Air is trying to come in the house as we're sending air out of the house.
So right now we're pulling in air through whatever leaks are available other places too.
As we go around and look for air leaks, if we feel air, it's coming from outside. We're not pulling air from room to room or from one portion of the house to the other. It's all coming from outside. So even if it's on an interior wall, that air is coming from outside somewhere.
So now we're on our way to find some leaks.
Right, and we're going to use a smoke gun. Typically I use my hand. If you can feel air move across your hand, that's fine. But for demonstration, we also have a smoke gun. And the smoke will let us see where we go. We've got some can lights here in the bathroom. Now, can lights are typically definitely breaks in the vapor barrier, breaks in your thermal boundary, where you've got this item that's pushed up into there, and these tend to leak a lot too. So it's rising up because of the heat from the light, and then it's hitting the air and getting blown down. We're kind of reversing what we typically see in a home. We're pulling air in from the ceiling, where typically hot air is rising and heading out through the ceiling.
The soffits like this one might be a typical area where you'd see the air leakage because it wasn't sealed years ago when they built the place.
Correct. We don't really know without looking in the attic or taking parts of this apart how this was built. Is the vapor barrier going all the way across here at the roof line, or does it stop here and then they tried to bring it down and over? Or did they just leave a void in here, and from above then we can get up there and look and air seal this whole soffit area that you can get to?
But for starters, we know we've got a problem, so.
We know we've got air leakage up there, yes.
Okay.
This is an interior outlet. We wonder, why do we have air coming through this? And as you can see, it's blowing, the air is being blown right into the house. This is an inside wall, but it acts as a chimney. There's penetrations here in the wall where the electrical is. There's gaps under the sheetrock here. There can be gaps at the top or at door frames. And so this becomes a chimney for warm air to rise up into this wall and head up into the attic at the top plate, and then take warm air and moisture into the attic. And it's important to seal areas, mainly from the attic if you can get there, to stop that moisture from getting into the attic, causing degradation to the material and frost build up in the attic. Interesting, we do have some airflow. No, we don't. It just feels cool there. Where are we getting all our air from in here?
Ah, there we go.
So we've got our rim joist here, which is the floor joist is going across, covered on the bottom with any kind of material and on the top with your flooring. And we can see here where we've got a gap, we can feel some air movement in there along the rim joist. Now, this is a good indication of an area that we have air loss, we have air leakage, but without really tearing out part of the ceiling, you're not going to get to it and you're not going to be able to fix it. And it's a hard area to get to from the outside. So just because we can pinpoint the leaks doesn't mean in older homes we can always work on them. A lot of times people feel their biggest air leaks are around their windows. And this one actually has air leaks around it because of the framing and just the old style window. A lot of windows don't leak as much as people tend to think they will. They're better sealed, they close better. Windows are cold. You can get drafts around windows just from convective loops. So the blower door is nice because it kind of pinpoints the areas to the homeowners to show them what is leaking and what isn't. You can really feel it coming through here. So here's another part of the rim joist that is exposed. We've got cobwebs moving in the back there. Another bad thing about this is it's also right near water pipes or boiler pipes. So it's a potential freeze zone there. And once you close these cabinet doors, it can isolate that area even more.
At least this is one spot you could at least get in there and do some air sealing and some insulating, unlike what we saw earlier. So
good point. At least in this small area you can get it. And people say, well, I can't, it's only a small area. It's still worth doing.
Yeah,
it all adds up.
That's quite a bit coming in through there.
Garages tend to have fewer leaking paths, but they have some large leaks, such as garage doors and heating systems. So let's go see what we have there. So here we've got an exterior door. And we can see the smoke is just kind of hanging around, even though that's a big crack. There we go, right at the end, we've got some air leakage. But really, that's not the problem in the garage. That's sealed pretty well. We have an electrical panel box here, which is, again, pathways leading to the attic, where the top plates may or may not be sealed, or the electrical outlets may or may not be sealed. And so we've got airflow through there.
Yeah, I can just feel that air coming out of there.
Other typical joints of leakage can be around the chimney stack, and you can see the air moving in there, although it's really not as bad as we see in a lot of spots. There it is there. That's where it's pouring in from here and needs to be properly sealed from either inside by dropping the ring. This ring won't drop. It needs to be sealed from outside, from the attic area. Somebody's actually been stuffing fiberglass in this door probably because of problems. Although the door itself isn't too bad. What's bad is the framing around the door, where the air pours right in. The AquaWarm program will give us an energy rating for the home, and through the Improvement Options Report, help pinpoint what is most cost effective to complete in the house that's been rated.
So we've got the report here, and it's given us a breakdown of the heating costs by the different components in the building. So it's telling us, you know, how much energy we're losing through the floor, through the wall, through the doors, through the windows, and it's got dollar values associated with all that. It's not showing us necessarily air leakage very clearly. So I guess that would be one of my questions, is how do you factor the air leakage into the overall cost, and are there any other considerations there?
There are. The air leakage is figured through the volume of the house and the blower door, and it'll give us a percentage here on whether the house is underventilated or overventilated. Do we need more ventilation? Do we need more moisture taken out of the house? How many occupants do we have? How many bedrooms do we have? It all goes into the factor of, does the house need more ventilation?
So it's kind of a balancing act between energy savings, yet making sure that the occupants stay healthy.
Doesn't do any good to air seal a house, make it tight, and all of a sudden have large amounts of mold building up, or indoor pollutants from too many pets or candles or whatever start causing health problems in the house, because now you've tightened the house up. The big question is, why are you telling me to tighten my house up and then to ventilate it? And the reason being that build tight, ventilate right, let's make this envelope tight, and then let's control our ventilation so it's not heading out through ceiling paths, into the rim joist, or other areas where it can cause rot or degradation to the building.
So you're bringing in a measured amount of ventilation to just the right place where you need it, not depending on random leaks somewhere where it may not do anybody any good, but it's still going to cost you in heating bills.
Correct.
Okay.
Yes.
Well, that makes good sense.